Hello friends, welcome to our YouTube channel. Today we shall solve a DC network problem using 5 methods. Let us have a look at the problem. We have to determine the current IL flowing through the 30 ohm resistor. This circuit comprises of 3 independent energy sources. Therefore, we shall apply superposition theorem first. Later, we shall apply Thevenin's theorem, followed by Norton's theorem to determine the current IL. Later, we shall apply mesh current analysis method and node voltage analysis method to find the current IL. Unless specifically told, students may adopt any of these 5 methods. But they have to practice all these methods to decide which one will be suitable for them. First, we shall apply superposition theorem to determine the current IL flowing through the 30 ohm resistor. For this purpose, we shall consider one source at a time and find the current flowing through the 30 ohm resistor. Afterwards, we shall take algebraic sum of these individual responses to find the net response. First, we shall consider the 10-volt source acting alone. So, we shall short circuit the 20-volt voltage source and open circuit the 5 ampere current source. Now, we shall determine the current IL1 flowing through the 30 ohm resistor. In this circuit, we find 15 ohm and 30 ohm resistors are connected in parallel. The equivalent resistance will be 15 parallel with 30 equals to 15 into 30 divided by 15 plus 30 equals to 10 ohm. Now we find the 4 ohm and 6 ohm resistors are connected in series. With this series branch, 10 ohm resistor is connected in parallel. The equivalent resistance will be 4 plus 6 parallel with 10 equals to 10 by 2 equals to 5 ohm. Now this 5 ohm resistor is connected in series with the 10 ohm resistor. With this series branch, we find this 10 ohm resistor is connected in parallel. With these two parallel branches, the series combination of 7 ohm and 3 ohm resistor is connected in series. Now let us reconnect the 10 volt voltage source. The equivalent resistance may be written as Req1 equals to 3 plus 7 plus 10 parallel with 4 plus 6 parallel with 10 plus 15 parallel with 30. That is equal to 10 plus 10 parallel with 5 plus 10, that is equal to 10 plus 6 equals to 16 ohm. Now let us determine the current delivered by the 10 volt source IS1. This is equal to 10 divided by Req1. Using the value of Req1, we get 10 divided by 16 equals to 5 upon 8 ampere. Now let us determine the current IP1 flowing through the rightmost parallel branch. IP1 equals to 10 divided by 10 plus 15 into IS1. Using the value of IS1, we get 2 by 5 into 5 by 8 equals to 0.25 ampere. This 10 ohm resistor is nothing but the parallel combination of 15 ohm and 30 ohm resistors. Therefore, this current IP1 gets divided into two portions. Our load current IL1 equals to 15 divided by 15 plus 30 into IP1. Using the value of IP1, we get 1 upon 3 into 0.25. That is equal to 0.0833 ampere. Now we assume that the 20-volt source is acting alone. Therefore, we shall short circuit the 10-volt voltage source and open circuit the 5 ampere current source. Now we shall determine the current IL2 flowing through the 30 ohm resistor. Here the 15 ohm and 30 ohm resistors are connected in parallel. The equivalent resistance will be 15 parallel with 30 equals to 10 ohm. Here 4 ohm and 6 ohm resistors are connected in series. With this series branch, 10 ohm resistor is connected in parallel. The equivalent resistance will be 4 plus 6 parallel with 10 equals to 5 ohm. Now these 5 ohm and 10 ohm resistors are connected in series. With this series branch, series connected 7 ohm and 3 ohm resistors are connected in parallel. With these two parallel branches, 10 ohm resistor is connected in series. Now let us reconnect the 20 volt voltage source. Now we shall determine the equivalent resistance Req2, that is equal to 10 plus 3 plus 7 parallel with 4 plus 6 parallel with 10 plus 15 parallel with 30, that is equal to 10 plus 10 parallel with 5 plus 10, that is equal to 10 plus 6, that gives us 16 ohm. Now we shall determine the current delivered by the 20 volt source IS2, that is equal to minus 20 divided by Req2. Here negative sign is taken because the 20 volt source is having negative polarity on the top. Now using the value of Req2, we get minus 20 divided by 16, that is equal to minus 5 upon 4 ampere. Now let us determine the current IP2 flowing through the rightmost parallel branch, that is equal to 10 divided by 10 plus 15 into IS2. Using the value of IS2, we get 2 by 5 into minus 5 by 4, that is equal to minus 0.5 ampere. This 10 ohm resistor is nothing but the parallel combination of 15 ohm and 30 ohm resistors. Therefore, IP2 gets divided into two branches. Our load current IL2 equals to 15 divided by 15 plus 30 into IP2. Using the value of IP2, we get 1 upon 3 into minus 0.5, that is equal to minus 0.1667 ampere. Now let us assume that the 5 ampere current source is acting alone. So we shall short circuit the voltage sources, and now we shall determine the current IL3 flowing through the 30 ohm resistor. We find that delta ABC is hidden into this circuit. We shall convert this delta into its equivalent star. RA equals to 4 into 10 divided by 4 plus 10 plus 6 equals to 2 ohm. RB equals to 10 into 6 divided by 4 plus 10 plus 6 equals to 3 ohm. RC equals to 6 into 4 divided by 4 plus 10 plus 6 equals to 1.2 ohm. Now let us draw the equivalent star. Now we find that 10 ohm resistor is connected in parallel with the series branch of 7 ohm and 3 ohm resistors. Therefore, the equivalent resistance will be 7 plus 3 parallel with 10, that is equal to 5 ohm. Now we find 15 ohm and 30 ohm resistors are connected in parallel. The equivalent resistance will be 15 parallel with 30 equals to 10 ohm. Now let us reconnect the 5 ampere current source. Now IS3 equals to 5 ampere. This current gets divided into the two parallel branches. Now we shall determine the current IP3 flowing through the rightmost parallel branch. This is equal to 7 divided by 7 plus 13 into IS3. Using the value of IS3, we get 7 divided by 20 into 5, that is equal to 1.75 ampere. This 10 ohm resistor is nothing but the parallel combination of 15 ohm and 30 ohm resistors. Therefore, our load current IL3 equals to 15 divided by 15 plus 30 into IP3. Putting the value of IP3, we get 1 upon 3 into 1.75, that is equal to 0.5833 ampere. When the 10 volt source was acting alone, we have obtained IL1 equals to 0.0833 ampere. When the 20 volt source was acting alone, we have determined IL2 equals to minus 0.1667 ampere. When the 5 ampere current source was acting alone, we have found IL3 equals to 0.5833 ampere. Now let us apply superposition theorem to determine the total load current IL, that is equal to IL1 plus IL2 plus IL3. Using the values, we get 0.0833 minus 0.1667 plus 0.5833, that is equal to 0.5 ampere. Now we shall apply Thevenin's theorem along with Norton's theorem to determine the current IL flowing through the 30 ohm resistor. For this purpose, we shall first remove this resistor from this circuit. Now, this circuit contains 4 meshes. Let the mesh currents be I1, I2, I3 and I4. Now we shall apply Kirchhoff's voltage law to different meshes. From mesh 1, we get 20 I1 minus 10 I2 equals to 10 plus 20, or 2 I1 minus I2 equals to 3. From mesh 4, we get minus 4 I2 minus 6 I3 plus 20 I4 equals to 0, or 2 I2 plus 3 I3 minus 10 I4 equals to 0. Now, if we observe, we find that mesh 2 and 3 share a common current source of 5 ampere. Therefore, they form a super mesh. From this super mesh, we can write minus I2 plus I3 equals to 5 ampere. Applying Kirchhoff's voltage law to this super mesh, we can write minus 10 I1 plus 14 I2 plus 21 I3 minus 10 I4 equals to minus 20. The open circuit voltage as seen from output terminals AB, VOC equals to 15 times I3. We have 4 unknowns I1, I2, I3 and I4. We have obtained 4 equations. Solving them, we get mesh current I3 equals to 1.2 ampere. Using this value, we get VOC equals to 15 into 1.2 equals to 18 volt. This is our Thevenin's voltage. Now we shall short circuit the output terminals A, B. Let the short circuit current be ISC. Now the mesh 1, 2 and 4 don't get affected by this short circuit. Only the third mesh gets affected. Therefore, the first 3 equations remain unchanged. Now applying Kirchhoff's voltage law to the super mesh, we get minus 10I1 plus 14I2 plus 6I3 minus 10I4 equals to minus 20. Now solving these four equations, we get mesh current I3 equals to 3 ampere. We observe that short circuit current ISC equals to I3, that is equal to 3 ampere. This is our Norton's current. We have obtained Thevenin's voltage Thevenin equals to Voc equals to 18 volt. We got Norton's current IN equals to ISC equals to 3 ampere. We know Thevenin's resistance Thevenin equals to Voc divided by ISC. Putting the values, we get Thevenin equals to 18 by 3, that is equal to 6 ohm. This will be equal to the Norton's resistance Rn. Let us draw the Thevenin's equivalent circuit. This comprises of a voltage source of 18 volt in series with a 6 ohm resistor. Let us now draw the Norton's equivalent circuit. This comprises of a current source of 3 ampere in parallel with 6 ohm resistance. Let us now reconnect our load resistor of 30 ohm. Now let us determine the load current from Thevenin's equivalent circuit. IL equals to Thevenin divided by Thevenin plus RL. Putting the values, we get 18 divided by 6 plus 30, that gives us 0.5 ampere. Let us now determine the load current from Norton's equivalent circuit. IL equals to Rn divided by Rn plus RL into IN. Putting the values, we get 6 divided by 6 plus 30 into 3, that is equal to 0.5 ampere. So we observe that the load current obtained from the Thevenin's equivalent circuit is exactly equal to the load current obtained from the Norton's equivalent circuit. Let us determine the current flowing through the 30 ohm resistor using mesh current analysis method. In this circuit, 30 ohm resistor is connected in parallel with 15 ohm resistor. The equivalent resistance of this parallel combination will be 15 into 30 divided by 15 plus 30 equals to 10 ohm. Let us now replace the parallel combination with this equivalent resistance of 10 ohm. Now the circuit contains 4 meshes. The mesh currents be I1, I2, I3 and I4. Let us apply Kirchhoff's voltage law to the different meshes. From mesh 1, we get 20 I1 minus 10 I2 equals to 30, or 2 I1 minus I2 equals to 3. From mesh 4, we get minus 4 I2 minus 6 I3 plus 20 I4 equals to 0, or 2 I2 plus 3 I3 minus 10 I4 equals to 0. In this circuit, mesh 2 and 3 share a current source. Therefore, they form a super mesh. From this we can write minus I2 plus I3 equals to 5. Applying Kirchhoff's voltage law to this super mesh, we get minus 10 I1 plus 14 I2 plus 16i3 minus 10i4 equals to minus 20, or minus 5i1 plus 7i2 plus 8i3 minus 5i4 equals to minus 10. We have four unknowns, I1, I2, I3 and I4. We have obtained four equations. Solving these equations, we get mesh currents I1 equals to minus 0.25 ampere, I2 equals to minus 3.5 ampere, I3 equals to 1.5 ampere and I4 equals to minus 0.25 ampere. We observe that I3 current is flowing through the 10 ohm resistor, which is actually the parallel combination of 15 ohm and 30 ohm resistor. Therefore, the I3 current actually divides into two portions. The load current IL equals to 15 divided by 15 plus 30 times I3. Putting the value of I3, we get 1 upon 3 into 1.5 equals to 0.5 ampere. Now let us apply node voltage analysis method to determine the current flowing through the 30 ohm resistor. This circuit contains four nodes. Let us select the fourth node as reference node. Therefore, the corresponding voltage V4 equals to 0. The node voltages V1, V2, V3 are considered as variables. Let us apply Kirchhoff's current law at the different nodes. At node 1, we assume the currents are flowing away from the node. Therefore, V1 minus 10 divided by 3 plus 7 plus V1 plus 20 divided by 10 plus V1 minus V2 divided by 10 plus V1 minus V3 divided by 4 equals to 0. Or we can write 0.55 times V1 minus 0.1 times V2 minus 0.25 times V3 equals to minus 1. At node 2, we assume that the currents are flowing away from the node. Therefore, IL plus V2 by 15 plus V2 minus V1 divided by 10 plus V2 minus V3 divided by 6 equals to 0. The load current IL is flowing through the 30 ohm resistor and this resistor is connected to node 2. Therefore, IL equals to V2 by 30. Using this expression, we get minus 0.1 times V1 plus 0.3667 times V2 minus 0.1667 times V3 equals to 0. At node 3, 5 ampere current is entering the node, whereas the other two currents are assumed to be away from the node. Therefore, V3 minus V1 divided by 4 plus V3 minus V2 divided by 6 equals to 5, or minus 0.25 times V1 minus 0.1667 times V2 plus 0.4167 times V3 equals to 5. We have three unknowns V1, V2 and V3. We have obtained three equations. Solving these equations, we get node voltages V1 equals to 12 volt, V2 equals to 15 volt and V3 equals to 25 volt. Using the value of V2, we get load current IL equals to 15 by 30, that gives us 0.5 ampere. So today we have solved a DC network problem with 5 different methods. Unless specifically told, you can adopt any of these methods to solve this kind of circuit problem. But you have to practice all these methods to decide which one will be easier for you. That's all I have for you today. Hope you have found this lecture useful. If you have any question or suggestion, please drop it in the comment section below. If you have liked this lecture, give it a thumbs up and share it with your friends. Thank you.